Working principles of DC motors used in household appliances and factories. DC motors, direct current motors, are widely used in both household appliances and industrial machinery due to their ability to provide precise control over speed and torque. The working principle of DC motors is based on the interaction between a magnetic field and a current-carrying conductor. Here's a detailed explanation of how DC motors function. 1. Basic principle. The basic principle behind a DC motor is electromagnetic induction. When a current flows through a conductor, usually a wire, and this conductor is placed in a magnetic field, a force is exerted on the conductor. This force is known as the Lorentz force and it causes the conductor to move. In the case of DC motors, this current-carrying conductor is the armature, rotating part of the motor, and the force causes it to rotate. The motor's armature is placed within a magnetic field created by either permanent magnets or electromagnets, field windings. The interaction of the magnetic field and the current in the armature windings generates a torque that drives the motor's rotation. 2. Key components. 1. Armature. The rotating part of the motor, consisting of a coil wound around a core. 2. Commutator. A rotary switch that reverses the direction of current flow in the armature windings to ensure continuous rotation. 3. Brushes. Conductive materials, usually carbon, that maintain electrical contact with the rotating commutator. 4. Field windings, or permanent magnets. These create the magnetic field in which the armature rotates. 5. Power supply. Provides the direct current to the motor. 3. Operation. Current flow. When DC voltage is applied to the motor, it supplies current to the armature windings through the brushes and commutator. Magnetic field interaction. The current flowing through the armature windings generates a magnetic field around the armature. This field interacts with the magnetic field from the field windings, or permanent magnets, exerting a force on the armature due to the Lorentz force law. Torque generation. The interaction between the magnetic fields produces a torque that causes the armature to rotate. The torque is proportional to the current passing through the armature and the strength of the magnetic field. Commutator action. As the armature turns, the commutator reverses the direction of the current in the armature windings at the correct moment. This reversal ensures that the armature continues to rotate in the same direction, as it ensures the force remains in the same rotational direction. Continuous rotation. The armature keeps rotating as long as current is supplied, with the commutator switching the direction of current to maintain continuous motion. 4. Speed control. 1. Field control. By changing the strength of the magnetic field, by varying the field current or using different magnetic materials, the speed of the motor can be controlled. 2. Armature control. Adjusting the voltage supplied to the armature can also control the speed of the motor. 3. Pulse width modulation, PWM. In modern DC motors, particularly in appliances and industrial systems, PWM is used for efficient speed control. 5. Direction control. The direction of rotation can be changed by reversing either the direction of current in the armature or the polarity of the field winding. This is commonly achieved by changing the connections to the power supply. 6. Types of DC motors. There are various types of DC motors, each with specific characteristics suited for different applications. 1. Permanent magnet DC motor, PMDC, uses permanent magnets for the field and is commonly used in small appliances like fans, toys, and computer peripherals. 2. Shunt DC motor. The field windings are connected in parallel with the armature, providing good speed regulation. 3. Series 600 motor. The field windings are connected in series with the armature, providing high starting torque, often used in heavy-duty applications. 4. Compound DC motor. A combination of series and shunt winding arrangements, offering a balance of high starting torque and good speed regulation. 7. Applications in household appliances. 1. Fans and blowers. DC motors are commonly used in fans and ventilation systems, where speed control is essential. 2. Washing machines. Many modern washing machines use DC motors for quieter, more efficient operation. 3. Power tools. DC motors are often used in drills, saws, and other portable tools, thanks to their variable speed and torque capabilities. 4. Toys and small devices. Many battery-operated toys and gadgets use small PMDC motors. 8. Applications in factories and industry. 1. Conveyor systems. DC motors provide precise speed and torque control for conveyor belts in manufacturing lines. 2. Robotics. DC motors are used in robots for precise movement control and speed regulation. 3. Electric hoists and cranes. DC motors are used for lifting heavy loads due to their high starting torque. 4. Pumps and fans. In industrial applications where adjustable speed is crucial, DC motors provide efficient solutions.